Welcome back, everyone. Ready for another deep dive?
Always.
Great! Today, we're going to tackle one of the giants of physics, Niels Bohr.
Ooh, yeah, poor.
Specifically, his groundbreaking work on atomic theory in those early years of the 20th century.
The dawn of quantum mechanics. Exciting times.
Absolutely. So picture this. It's 1913, and the world of physics is, well, kind of in chaos.
A little bit, yeah, discoveries flying left and right.
Like what?
Well, you've got radioactivity, for one.
Yeah.
Completely revolutionized how we understood the atom.
Right, and then there were these strange line spectra coming from different elements. Scientists were baffled.
Puzzling those were. And of course, Einstein's theory of relativity was shaking things up even further.
It was like the whole foundation of classical physics was cracking. And right in the middle of this upheaval comes Niels Bohr.
With his revolutionary ideas about the atom.
Exactly. Now, his journey actually started a bit earlier, trying to understand how alpha particles collided with atoms.
Yeah, that was heavily influenced by his time with Ernest Rutherford. Rutherford had just proposed the idea of a nucleus.
Right, the nucleus at the center of the atom. So how did Bohr initially picture the electron in all of this?
Well, you might find this surprising, but he actually imagined it as being stationary.
Stationary, really? That's so different from how we think of electrons today, whizzing around the nucleus.
It does seem counterintuitive now, but remember, this was the very early days of atomic theory. They were still trying to figure out what an electron even was.
So much we take for granted now was completely unknown back then.
Exactly. Bohr was working with limited information, making assumptions based on what little they knew at the time.
And he wasn't afraid to revise those assumptions as new evidence emerged. That's what makes his work so compelling, I think.
Definitely. Always adapting and refining his ideas. Now, this brings us to 1913, when Bohr publishes his famous trilogy.
Ooh, the trilogy.
A series of papers that, in essence, laid the foundation for quantum theory.
This is where things get really exciting.
Right. In these papers, Bohr takes a huge leap. He combines classical mechanics with Planck's quantum theory.
Whoa, that's a big deal. Those were two very different worlds at the time.
They were. But Bohr saw a way to bridge them. He took the familiar idea of planets orbiting the sun and added this revolutionary twist.
He proposed that electrons couldn't just exist anywhere around the nucleus. Instead, they could only occupy specific energy levels.
Like steps on a staircase. You can't be halfway on a step.
And those steps, those energy levels, were determined by Planck's quantum of action.
That's the genius of it. By quantizing the energy, Bohr could beautifully explain those line spectra that had scientists scratching their heads.
You mean those distinct colors of light emitted from different elements? Not a continuous rainbow, but specific lines?
Exactly. His model wasn't just explaining what was already known.
Yep.
It predicted colors that hadn't even been observed yet.
And those predictions were later confirmed by experiments? That's impressive.
It is. Talk about predictive power.
What always strikes me is how Bohr achieved all this with relatively simple assumptions. Simple, yet revolutionary. He even laid them out clearly in his paper, like how atoms could remain stable without radiating energy, how they emitted light, and the crucial link between energy and frequency. He connected the dots in a way no one had before.
And that's how he cracked the code of the hydrogen spectrum. Then he set his sights on helium, even tried to apply his model to molecules.
Ambitious. Did his success continue?
Well, while his model was brilliant for simple atoms like hydrogen, it did start to hit some snags when applied to more complex systems.
Like those ring models he proposed for molecules.
Yeah, electrons arranged in neat little rings around a line connecting the atoms. A creative idea, but ultimately...
Didn't quite capture the complexity of how molecules really bond together.
Right. But even though his model had limitations, it gave rise to some fundamental constants that we still use today.
Like the Bohr radius, which describes the size of the hydrogen atom, and the Bohr magneton, a measure of an electron's magnetic moment.
Concepts that have a lasting impact on physics and chemistry even today. It was a huge leap forward, no doubt about it.
So he was on a roll, but then new challenges emerged. Electric and magnetic fields, for instance. We know they affect atomic spectra, right? How did his model handle that?
That's where things get even more interesting. Bohr knew about the Stark and Zeeman effects, how these fields could influence those spectral lines.
And he tried to incorporate them into his model.
He did. For electric fields, he envisioned electrons taking on elliptical orbits instead of perfectly circular ones.
I can picture those diagrams like electrons vibrating back and forth.
He even developed equations to describe those elliptical orbits and had some success explaining the Stark effect. But the Zeeman effect, the one with magnetic fields, that one proved a bit tougher.
So another puzzle to solve, another layer to peel back.
That's the beauty of science. Every answer leads to more questions, pushing us further down the rabbit hole. And in Bohr's case, his work, even with its limitations, ultimately paved the way for a complete revolution in physics.
The birth of full-blown quantum mechanics. Quite a legacy.
It is indeed. And we'll delve into that legacy in the next part of our deep dive. But for now, let's pause here and reflect on what we've learned about this remarkable physicist so far.
It's amazing how he started with a simple, almost intuitive model and ended up revolutionizing our understanding of the atom. He dared to challenge the status quo, combined classical and quantum ideas in a way no one had before. That's the essence of his genius, I think.
Beautifully said. And in the next part, we'll see how this daring spirit led to even more profound insights, setting the stage for the quantum world as we know it today.
Stay tuned, because our deep dive into the world of Niels Bohr is just getting started.
Definitely. There's so much more to uncover.
So before we took a break, we were discussing how Bohr's model, while groundbreaking, did encounter some challenges when it came to more complex systems.
True, but those limitations shouldn't overshadow the incredible impact of his work. I mean, even today, the principles he laid out are still fundamental.
Right. And this is where those 6 key postulates from his 1915 paper come in. They really capture the core of Bohr's thinking and form the basis for what we call old quantum theory.
Exactly. It's worth taking a closer look at them. The first one, well, it really throws classical physics for a loop. Bohr proposed that atoms have these special stationary states where they don't radiate energy, even though classical physics says they should be.
That seems counterintuitive. If electrons are orbiting the nucleus like planets, shouldn't they be constantly losing energy, spiraling inward? How did Bohr address that?
He suggested these stationary states were unique, allowed energy levels where the electron could exist without losing energy. Imagine it like the electron is on a specific step of a staircase. It can't be between steps.
Okay, so the electron is stable in these stationary states, but what happens when it emits or absorbs light? We know that occurs, right?
Right. And Bohr's second postulate tackles that. He states that light is emitted or absorbed only when an atom transitions between these stationary states. And the color of that light, it corresponds directly to the energy difference between those steps.
So that explains why we see those distinct colors in line spectra, not a continuous spectrum, because the energy levels are quantized. It all goes back to Planck's constant.
Absolutely. That relationship between energy and the color of light, or frequency, is given by that famous equation, E, where H is Planck's constant. This connection, this energy-frequency link, is a cornerstone of quantum theory.
So we have these stationary states, and we understand how light emission and absorption work. But what about the electron's motion within those states? Does classical mechanics still apply there?
That's where Bohr draws another crucial distinction. He postulates that while classical mechanics works fine to describe the electron's motion within a stationary state, it breaks down completely when describing the transitions between states.
So we need a new set of rules, a quantum set, to understand how those jumps from one energy level to another happen.
Precisely. And Bohr provides a key piece of that quantum puzzle with his fourth postulate. He states that the average kinetic energy of an electron in a stationary state is related to its orbital frequency and a whole number, m. This number, we call it the principal quantum number, it labels those steps on the energy staircase.
So essentially, it quantizes the energy levels, no in-between steps allowed.
Exactly. And his fifth postulate builds on this, addressing angular momentum. Bohr states that in the normal state of an atom, the angular momentum of each electron is equal to h to 2.
Ah, that equation. Every physics student knows that one.
It's iconic. But it's important to remember that Bohr himself was cautious about applying these classical concepts, like angular momentum, to the quantum world. He recognized that his model had limitations. In fact, he specifically states that this angular momentum quantization, it only works for circular orbits.
And we know now that's not really how electrons behave. It's more like these fuzzy probability clouds, not neat little orbits.
Right. And this is where later work by de Broglie and Schrödinger comes in, introducing the wave nature of electrons and a much more sophisticated description of their behavior.
But even though the specifics of Bohr's model have been refined, those postulates, particularly the quantization of energy and angular momentum, they led to a monumental shift in how we understand the universe.
They're stepping stones to the development of, full-fledged quantum mechanics. It's like Bohr opened a door to this whole new realm of physics.
That shift from certainty to probability in quantum mechanics, it's still mind-boggling, I think.
It is a profound shift. And Bohr himself grappled with these ideas throughout his career, especially in those famous debates with Einstein. Those were some pretty heated discussions about the nature of reality, whether God plays dice with the universe, as Einstein put it.
It seems like every answer in quantum mechanics just leads to more questions, more mysteries to unravel.
That's what's so captivating about it.
Yeah.
And Bohr, even with his model's limitations, he grasped some fundamental truths about the atom, truths that have stood the test of time.
His model, it may be simple, but it's profound, a great introduction to the quantum world. A way to understand those core concepts without getting lost in the mathematical complexities of the more advanced theories.
Exactly. And that's the beauty of his work. It's not just about getting the right answers, but about asking the right questions, daring to challenge existing paradigms.
He wasn't afraid to embrace new ideas, to blend the classical with the quantum, even if it seemed strange or counterintuitive at the time.
And that courage, that willingness to think differently, ultimately sparked one of the most significant revolutions in scientific history.
Couldn't have said it better myself. Before we wrap up, I have to ask, what if Bohr hadn't made that leap? Hadn't dared to quantize the atom? How different would our world be?
That's a fascinating thought experiment. Our technological landscape without quantum mechanics is almost impossible to imagine. Everything from lasers and transistors to modern medicine and material science. It all hinges on our understanding of the quantum world.
So no smartphones, no MRIs, no solar panels as we know them.
Many of these technologies might not exist, or they would be in a very, very primitive state without the foundation laid by Bohr and the subsequent development of quantum mechanics.
That really highlights the impact of his work. It's incredible.
It is, and it's not just about specific technologies. The whole scientific mindset shifted because of Bohr's work. Embracing uncertainty, accepting probability, the realization that the universe operates in ways that often defy our classical intuition. These are all hallmarks of quantum thinking, and they have implications far beyond physics.
Almost a philosophical shift in how we view the world.
Exactly. And that's what makes Bohr's legacy so enduring, I think. It's not just about the equations or the models, but a way of thinking, a willingness to challenge the status quo and embrace the unknown.
And as we continue to explore the quantum realm, Bohr's spirit of inquiry, his willingness to embrace both the simplicity and the strangeness of the universe, that will continue to guide us.
Absolutely. His work shows the power of human curiosity, our drive to explore and understand the universe around us.
You know, as we wrap up our deep dive into Bohr's world, I keep coming back to that question. What if he hadn't taken that leap of faith and quantized the atom?
It really is a mind-bending thought experiment.
It is. We talked about the technological side of things, but what about the scientific mindset itself? Could we have even reached the profound insights of quantum mechanics without Bohr's pioneering work?
Hard to imagine how. Bohr's willingness to, break from classical physics to embrace this whole idea of quantized energy levels was so radical for its time.
He basically shattered the old assumptions and opened up a whole new dimension for scientists to explore.
Exactly. His work gave others permission to challenge those deeply ingrained ideas about how the universe works, to consider that maybe, just maybe, things at the atomic level operate by a completely different set of rules.
And that shift in thinking led to this explosion of ideas and discoveries in the quantum realm. I mean, we wouldn't have things like quantum field theory or quantum computing or even a deep understanding of how stars work without it.
Absolutely. Bohr's work was like planting a seed that grew into this vast and intricate tree of knowledge.
It's also fascinating to think about how his initial model, while, ultimately superseded by more complex theories, still holds a special place in our understanding of the atom.
It does. It's a testament to the power of simplicity, finding that elegant core idea that unlocks a deeper understanding.
Like that first step on the staircase that leads to a whole new world.
And for a lot of people, Bohr's model remains that crucial first step into the quantum realm. It gives them a conceptual framework that makes these complex ideas accessible.
A way to grasp those fundamental principles without getting bogged down in all the mathematical details.
Exactly. I think it's one of the most important aspects of his legacy. He made these revolutionary concepts understandable, even inspiring.
And his influence goes beyond science itself. That spirit of inquiry, that willingness to challenge assumptions and embrace uncertainty has had ripple effects in so many areas.
Yeah, in philosophy, art, even our everyday ways of thinking about the world.
It encourages us to question, to explore, to remain open to the possibility that there's always more to discover.
Precisely. And that's maybe the greatest gift Niels Bohr gave us. A universe not of fixed certainties, but of endless possibilities waiting to be uncovered.
So, as we come to the end of our deep dive into the world of Niels Bohr, I hope you've enjoyed this journey through the birth of quantum theory and the impact of this remarkable physicist.
It's been a pleasure sharing these insights with you. And if our conversation has sparked your own curiosity about the quantum world, well, that's the greatest tribute we could pay to the legacy of Niels Bohr.
Until next time, keep exploring, keep questioning, and keep diving deep into the mysteries of the universe.
And never be afraid to challenge the status quo.